Okie doke. Oh, yeah, it does seem to work.
Okay, so welcome everyone. So today we have the pleasure of starting our session with Nima Arkani-Hamed, and he'll be telling us about building walls and draining swamps.
All right, well, it's wonderful to be back here at the IFT. This is as you'll see, it's a very apt title for this talk. It's too painful for me to use this title anywhere in my home country, but I thought I could use it here. I just want to start saying quickly, I remember over 10 years ago when I was lucky enough to be one floor up from Cumrun's office when he first started talking swamplandy thoughts. I say that I had two immediate reactions. One was that if one was going to try to make, if it's really true that there's something like a swampland, there had better be sharp statements. There had better be statements that involve equal signs, and not just squiggles. And the reason is that the entire point of the landscape, and certainly the entire practical point, is that there are all kinds of things that might naturally be true with a squiggle or order 1 relations between things. But the entire question is whether with fine-tuning or something, it's possible to make exceptions to those things that you would naively think are order 1 related to each other. So if there's going to be anything interesting, or if it's going to turn into to really a science eventually, there had to be sharp, specific statements that you could make about the structure of low-energy physics that would follow from some kind of consistency conditions in the ultraviolet. And I remember the first conversation I had with Carmen about it. I said, so what? Is there going to be something you can say about higher dimension operators? That's ridiculous. What could we possibly know about higher dimension operators from ultraviolet consistency? They are what they are. We have to go out and measure them. But of course, I became fascinated by the subject for a year or so back then. And out of our efforts with a number of us, there were a couple of these sharp statements, statements that are at least in principle falsifiable. One was not explicitly gravitational, although it deeply has to do with Lorentz invariance and unitarity, so it's tied to the consistency of gravitational theories ultimately, was a statement about the signs of higher dimension operators. Okay? So certain signs of some higher dimension operators have to be positive. So indeed, it's not ridiculous. There are some things you can say about higher dimension operators. And the other one was the weak gravity conjecture. And these are both things that are in principle falsifiable. At least precise enough versions of them are in principle falsifiable. They have specific numbers that you can go out and look for. And so let me just review some things. I'm sure these kinds of things have been said many times in this meeting. But what's the qualitative reasons we should expect that there's more we can say from consistency of a gravitational theory that we can't say in a sort of normal, what I like to call the crappy metal picture of the world as some kind of condensed matter system where there's perfect decoupling between the physics of very high energies and very long distances. Why is that false in the real world? It's false in the real world ultimately because of gravity, and ultimately because unlike garden variety physical systems, we know a lot about what happens with gravity at incredibly high energies because you make extremely large black holes. And we're all very used to it in this field, but it's kind of amazing that, in a sense, understanding what happens with the collision of particles at an energy 1000 M Planck is much easier than understanding what happened with neutrino electron scattering at energies much bigger than the weak scale before we knew about W's and Z's, right? There was one non-normalizable theory, and we knew absolutely nothing about what happened when you collided particles at very high energies until we came up with a UV completion, whereas it's not true for gravity. We know a lot about what happens when you collide particles at incredibly high energies. You make pretty big black holes, and they Hawking evaporate, and it's sort of details of exactly the phase correlations between the things that come out and so on that we know. But we know much more about the ultraviolet in a theory of gravity than we would in garden variety other kinds of theories. And so that goes along with all the words on the slide. just repeating what I said, is because extremely high energy collisions produce very large black holes, so, which then come back emitting very soft Hawking radiation. So incredibly high energy states are related to physics at very long distances. And we're used to, similarly, gravitational constraints on low energy physics, like these very rough holographic bounds, a number of degrees of freedom scaling exponentially at most of the area over g Newton rather than the exponential of the volume. So now, I think it's fair to say, though, that for a long time, certainly I thought, I think most people thought, that these deep gravitational things would only show up for very, very delicate questions. Okay, so they would not be, that if you took a random effective field theory, it would satisfy all these things. And it's only for very delicate questions about how the information comes out when you have an evaporating black hole, effects that look naively like they're exponentially small. It's for effects like that these deep gravitational consistency conditions would actually matter. And I guess the surprise and the interest, to some extent, of many of the kinds of questions that we've been asking since has stemmed from the realization that that may not be true, that there are impacts of this of ultraviolet consistency on more accessible, non-exponentially suppressed long-distance physics. So I won't repeat the logic that goes behind the weak gravity conjecture here, but I want one thing that I want to correlate it with is that all of these statements, that even the statements about holographic bounds involve an inequality. The weak gravity conjecture involves an inequality with a sharp coefficient. And so, and finally, if you think in terms of at least my favorite, one of my favorite sharp versions of the weak gravity conjecture, which is the claim that the mass-to-charge ratio of extremal black holes should always be pushed down by the effect of higher dimension operators, that again implies a very specific set of signs for things that go beyond the two-derivative approximation. So many of these criteria, these novel restrictions on low-energy effective field theory, are associated with some notion of positivity. And let me remind you of the other notion of positivity from this, this period of over a decade ago now, that just locality and really Lorentz invariance and locality, which means causality and Lorentz invariance and unitarity imply positivity restrictions on higher dimension operators in effective field theory. So an example is if we take free Maxwell theory and we add a higher dimension operator like f to the fourth, then these coefficients have to be positive for a very simple reason that if you turn on translationally invariant backgrounds like constant electric or magnetic fields, in these translation invariant backgrounds, these higher dimension operators can actually affect the speed of propagation of small perturbations on that background, and they can make things go faster than light, even if you make the background arbitrarily small. Okay, so that's the usual reason it's possible to say something about higher dimension operators is when they violate something which is sort of critical or zero in the two-derivative approximation. That's why we look for proton decay, because the long-distance world of the standard model at two-derivative level has baryon number as an accidental symmetry. Similarly, in any Lorentz invariant theory at two-derivative approximation, everything propagates exactly on the light cone, and so it's dangerous. You might imagine that higher dimension operators could push you inside or outside the light cone, and so you can say something about the higher dimension operators. And there's also a more direct way we'll review and greatly generalize in a second that relates this to via dispersion relations to causality in the analytic properties of the S matrix that control both causality and unitarity in the ultraviolet. So this is the sort of infrared avatar. The superluminality is the infrared avatar of actually a deeper problem and more statements that you can make at high energies following from unitarity and causality. So we'll be really generalizing that in the rest of the talk. Now, I want to point out that this positivity and the weak gravity conjecture are related to each other. And it's because even though this is not a gravitational statement, protecting subluminality is crucial for the physical consistency of horizons. It's a very bad idea to be able to go faster than light, because that makes it impossible to to unambiguously talk about what a horizon is gravitationally. If you can't unambiguously talk about what a horizon is, then every notion of black hole thermodynamics is dead. And it's interesting that there is a real correlation between the theories that violate bounds like this and in many examples, and things that violate the second law of thermodynamics when you turn gravity on. And concretely here, if you turn on and after the fourth operator, you can compute what it does to the mass-to-charge ratio of an extremal black hole, and only when it has the right sign does it push the mass-to-charge ratio of extremal black holes down, as the weak gravity conjecture would want you to do. Okay? All right. Now, so at least for me, this was my first flirtation with positivity in a very trivial way. These are really, really trivial things. I mean, the ideas are extremely simple. And then I spent the last sort of 5 to 10 years in a much fancier interaction with the notion of positivity. And if you've had the misfortune to hear me talk about scattering amplitudes ad nauseum for the past 5 or 10 years, much fancier kinds of positive words have made an appearance. The positive Grassmannian, talk about matrices with minors that are all positive, all kinds of fancy schmancy positivities. And they appear to have absolutely nothing to do with this older set of ideas, except the following. So in the previous story, why are things positive in physics? We've seen many things are positive in physics, and the ultimate origin of positivity is one of two things: the positivity of probability and the positivity of energy. Those are two obvious things that are positive, and they imply many other things later. Well, one of the, to me, fascinating aspects of this story of positive geometry in scattering amplitudes and now in cosmology and in other places is that the logic is inverted, and there's some positive structure that implies locality and unitarity. It's not locality and unitarity are the kings, and they imply some positivity. It's the other way around. Positivity is king, and it implies, as an outcome, in all the cases, in the cases that we understand, locality and unitarity, and many things besides. Okay? So it at least awakens in your mind the possibility that there's more positivity out there than is forced on you by the concepts that we're used to. Okay? So that's the only link is that this positivity implies locality and unitarity. And so that's what inspired my friends and I to go back after all this fancy experience to the old story to see if there was more positivity there than we realized. Okay? And there is. That's why I'm giving this talk. Okay? So there is actually an infinite amount of extra things you can say about effective field theory. And I skipped this over, but there's by now in this fancier direction. By now, there's a number of examples of these positive notions. Started off with this sort of fanciest object related to n equals 4 super Yang-Mills amplitude, the EFTHedron. In the past year, we've seen the same kind of geometric ideas show up. Nothing to do with integrability, nothing to do with supersymmetry, phi cube theory, theories of pions and gluons in any number of dimensions that are associated with. Now, these objects are mathematically new. These are sort of beautiful old mathematical objects that have been sitting around for 40 or 50 years. And even more recently, in the calculations of the wave function of the universe in perturbation theory, these things are taught in a very similar, conceptually similar way to these positive geometric spaces. But the inspiration to go back and look at these old positivities has now yielded two new things, two new appearances of the same kind of ideas. The one I'll talk about here today is, which we call the EFTHedron, which is a hidden positive geometry of causality and unitarity. And I will have zero time to talk about it, and it's not really of interest to this conference, and is, I think, of fundamentally less interest than this anyway. I don't really care that much about conformal field theories. But there's an analogous structure for conformal field theories. Once you see this structure for effective field theory, it's obvious what to look for in CFTs as well. All right. Okay, so what I'm going to talk about is this EFTHedron. This is work in progress with Yutin Huang and Chuchu Huang. And this is a universal geometry controlling effective field theory. And in particular, infinitely many quantitative predictions about quantum gravity in the real world. Okay? So we'll talk about graviton scattering, photon, graviton scattering. As you'll see, we're going to make infinitely many predictions for things nobody cares about. Okay? So, so it's 0 times infinity in its importance. And whether you get 0 or 1 or 10, product of those things depends on how you take the limit. Okay, so let me talk about the cast of characters. And I'm going to talk about this a little bit loosely now, just for time. The cognoscenti, the experts in the audience who will ask me about cuts that come all the way down to 0 and the running of operators in low energy theory, we can talk about that later. Okay, but I'll just say it just so you have the 0th order idea of what we're talking about. So imagine you've integrated out some massive particles. It could be strings at tree level. It could be any quantum field theory at loop level. You integrate out a bunch of massive particles. And we want to talk about the higher dimension operators in this theory. So the whole idea is we're going to say something about higher dimension operators. Now, higher dimension operators are not invariant things in a Lagrangian, because you can do field redefinitions, et cetera, et cetera. The real invariant thing are the contact pieces and scattering amplitudes. Okay, so that's how we identify higher dimension operators. For example, that's how you construct the higher dimension operators in string theory. You calculate the tree level scattering amplitude, you pull off the contact pieces, and then you find a Lagrangian that matches them, right? So let's imagine that we're doing that. We're taking the low energy amplitude. No matter what particles I have on the outside, there's a factor that takes care of the spins of the particles. Here I'm assuming they're identical. Also, I didn't say it, but I'm talking about amplitudes of the form AB goes to AB. So it doesn't violate any symmetries. Okay, it's something, and therefore it's something that could be controlled by unitarity as well, because the initial and final states have the same quantum numbers. All right. So now I'm interested in the contact piece of the scattering amplitudes, and I'm going to write them like this. A sum of just 2 to 2 scattering, so S to some power, T to some power, and I will organize them by the total dimensions of this amplitude, or the total dimension of the operator capital D. So it'll be S to the D minus Q, T to the Q. Right? There are these coefficients. And of course, these things have units. So let me write it as something that carries the units and something that's dimensionless, okay? So in other words, those A hats are ratios of the things with different, of the different powers of S and T with the same overall dimension, and T is the sort of overall weight of the whole thing. All right, so here's all the data that there is. I'm doing it this way just for the convenience of this talk. There's really more fundamentally a statement just about that guy, but this will make it convenient to talk about. So this is the data, if you like, the overall scale of these higher dimension operators and their relative sizes. Okay? Now, what is the intuition that there has to be more we can say about these guys? Well, this thing that some of them are positive is just kind of pathetic, right? Surely there's more you can say, because on the one hand, if I told you that you have dimension 6 operators that are suppressed by a TeV, you would not expect the dimension 8 operators are suppressed by 1,000,000 TeV. You know, you'd expect that everything is roughly suppressed by the same scale. So that's one expectation. The other expectation is if you have a whole bunch of dimension 8 operators, you can't make one of them 1,000,000 times bigger than the other. They should all be roughly suppressed, again, have roughly the same size. So those are two pieces of intuition that, again, you might think, well, maybe that's naturalness that tells you that. Maybe you could fine-tune to make one of them 1,000,000 times bigger than the other, and so on. Okay? So what we're going to talk about is exactly something that actually quantifies those two pieces of intuition and tells you that, indeed, there are some specific walls in the space of couplings. Okay, so that's the walls that we're going to build. The specific walls in the space of couplings, and you have to lie inside those walls. Okay? Both for, and from what I just told you, there have to be two kinds of statement. One, there have to be nonlinear statements that link operators of different dimensionality, because I can't just say a dimension 8 operator's got to be comparable to the dimension 6 operator. They have different units. The only statement that I could make has got to involve products of operators of different dimensions, such that you can make a sensible statement where everything has the same units. Okay? So you should expect nonlinear relations between these T's, and you might expect linear relationships between these A hats. All right? Because they have the same units. And that's exactly what we're going to see. We're going to see that these T's satisfy infinitely many nonlinear inequalities, and that these A hats lie inside very specific geometric shapes. You see, these A hats are naturally projective. You can think of them as points in a projective space because only the ratios matter. They're defined up to rescaling. So these coefficients have to lie in very specific polytopes. Okay? And both of these are the special cases of a more general statement that this whole matrix of numbers, if you remove the hats, the whole matrix of numbers has to lie in a very specific geometric shape. That's the EFTHedron. Okay? But I'll describe sort of various slices through the EFTHedron so you see what it looks like. And then I'll give you some examples for the standard model at the end. All right. How am I doing for time? Really crappy. Sorry. Is there a clock somewhere in the room? Huh? I have 10 minutes. All right. Very nice. All right. So let me give you an idea for both, for where both statements come from. So first, but let me remind you causality and unitarity tell us. Now, famously, to this day, we don't know if someone hands you a 2 scattering amplitude, say, here's the whole amplitude, there, and say, check, is it right or wrong? We don't know how to do it. Okay? It's amazing that we know all sorts of other fancy things. We know the rules for consistency of Euclidean conformal field theories. We can do all kinds of stuff like that. But a physical question about the real world, we don't know the answer to. Not even in perturbation theory do we know the answer. Okay? The heart of the problem is the physical one. How do you know from this asymptotic data, you sent the particles in, they collided, they came back out. How do you know whether what happened on the inside was causal? How do you, now we know how to check unitarity, we know how to check Lorentz invariance. But that is trivial. I can write down 1 million non-perturbative S matrices for you, which are which are unitary and Lorentz invariant, but are garbage. Okay? That cannot possibly come from reasonable causal physics. And so that was the heart of the S matrix program in the 60s, was that somehow the analyticity properties of the S matrix are supposed to encode causality. Unitarity and Lorentz invariance are trivial. They're supposed to encode causality. And that's the problem. We don't a priori know what those rules are. So what people did is they cheated. They stared at Feynman diagrams to get an idea what the analytic properties were like, and then pretended that they didn't do it, and went and see, is this enough to determine the answer? And no, it's still not enough. We'll go cheat and look some more. Okay, so, okay. Now, for 2-point functions, the situation is much better. And we've known since the 1800s. What is the properties of a Green's function that reflects something that's causal in position space? So the property of Green's function in energy space that reflects causality in position space. And for that reason, we also know something about scattering amplitudes, the analytic properties of scattering amplitudes, in a limit. And this is the limit that effectively turns it into a 2-point function, where you have 2-to-2 scattering when t is fixed and very small, so that effectively you have the propagation of one particle in the sort of a background set up by the other. Okay? So in this limit, a 2-to-2 scattering amplitude is very close to a 2-point function, and therefore we do know what the analytic properties are. And here are the properties, that you should only have singularities on the real axis, no singularities anywhere in the complex plane other than on the real axis, maybe a pole for stable particles, a branch cut. And importantly, that the amplitude, causality tells you the amplitude to be bounded by power of s at very high energies. This is at fixed t. At fixed t in this Reggie limit, when s goes to infinity, the amplitude has got to be bounded by power of s. The power of s cannot exceed 2, and it's equal to 2 if the theory has gravity. It's equal to 1 if the particle you're scattering is charged under a photon or a gluon at very high energies, and otherwise is 0. Okay? So that's what we know about the analytic properties of the S matrix. And that is enough to allow you to write down, and this is supposed to be an expression that's valid for all S and fixed small t. Okay? For all S fixed small t, you can write down, just Cauchy's theorem lets you write down a formula like this. So there are these subtraction terms that take into account maybe the amplitude could have grown up to s squared as you go to infinity. So let's not worry about those. But here is the business part, is that you can write it, Cauchy guarantees you can write it the sum over poles, simple poles in S, where the sum might be an integral. This might be a branch cut. Okay, so that sum could be an integral. This looks a lot like a Challen-Lehmann representation for a 2-point function, but it's about an amplitude for 2-to-2 scattering. And it's because, again, we've gone to a limit where the amplitude is essentially a 2-point function. All right? So that's what causality tells you. It tells you that we have an expansion that looks like this. And furthermore, this residue at s equals m squared here, when written as a function of cos theta, which is 1 plus 2t over m squared, that residue must be expandable in terms of Legendre polynomials with positive coefficients. So there are two things that we know. The positivity of energy is that the m squareds are positive, and the positivity of probabilities tell us two things. First, these coefficients are positive in the expansion in Legendre polynomials. Well, that's it. It tells us that we can expand them in terms of Legendre polynomials, or they're called Gegenbauer polynomials, in general number of spatial dimensions with positive coefficients. Okay, so notice that the character of problem that we're solving is that we have something that depends on some variables, and forget these pieces for a sec. It's written as a sum over pieces, sum over some objects with positive coefficients. Okay? So every time you run into this kind of question, so if nothing else from this talk, from the 5 minutes I have left, you should take this away, that every time you run into a problem where you have some object that's expressed as a positive combination of a set of standard basis objects, the usual physicist attitude is to sort of dot it into something and make an inequality that something is positive. But what you should do instead is relax and let the objects tell you what to do instead. Okay? Because this is a problem about polytopes. Okay? Every time you see this question, that you have something which is expressed as a positive sum of a set of objects, it's actually telling you that the thing that you're interested in lives inside a particular geometric shape. And here's polytopes 101. So if someone hands you a bunch of vectors and says to look at any point which is a weighted sum of these things, then any point on the inside is a polygon expressed like this, where all the weights are positive. It's much better to think about all these things projectively. So you imagine you go to one higher dimension, you add a 1 to the top of all the vectors. Now these are things that live in a projective space. And the beauty of doing that is that now this is a statement that this projective object is just a positive combination of these basic vectors. Okay? You don't have to divide by the W1 through Wn. So that's typically the way the problem is given to us, is we're typically given the weighted sum of a bunch of objects. So this is a bunch of vectors. This is the convex hull notion. But this is not practical for checking whether some point is inside or not. So if someone hands you some A and says, is it in there, is it not in there, it's not easy to check whether you can write it like this. What you need instead is another description of the same thing, which is that you can cut out the shape by giving all these inequalities. Okay, you can give all these inequalities on the right side of that line, and that line, and that line, and so on. So that's the so-called facet description of the polytope. And so that's giving a bunch of linear equations that have to be greater than 0 that cut it out. Now, this is in general, there's a systematic way to go from the text description to the facet description, but it's hard. Okay? I mean, it involves doing lots and lots of computations. And so that's why linear programming exists as a subject, is to help you do this numerically in many cases. But mathematicians have been studying polytopes for 50 years, 70, 80 years. And what it means to understand a class of polytopes is exactly this: to understand everything about its facet structure ahead of time, okay, without doing this systematic work. And there is a very special class of polytopes that are extremal in many ways, that are associated with an ordering. And this actually takes some inspiration just from polygons. So all polytopes on the plane are just convex polygons. Everything is just a convex polygon. And in a convex polygon, the vertices are naturally ordered. So you have 1, 2, 3 going around the polygon. So it's not obvious how to, if you have a higher dimensional polyhedron, there's no obvious ordering to the vertices. But there is a class of polytopes that are associated with an ordering. So if you give me vertices v1 through vn and they're ordered, then I should have said here that everything about the structure of the faces is controlled by computing these determinants. All these determinants made up out of these vectors check whether these guys, if this determinant is positive, it means that, for example, A1 is on the right side of the plane made out of A2 through AD. If it's negative, it's on the left side. If it's 0, it's coplanar with all of them. The information about all those signs tells you everything about what the face structure of the polytope looks like. And so this very special class of polytopes is the one for which, once you give the ordering, all of these determinants are positive. And so there are many words associated with this. You would say that the matrix is totally positive. This matrix of, if I just stack these vectors together in a matrix, I'd say the matrix is totally positive, or it's in the positive Grassmannian. And if I take the convex hull of all vectors of this form, that's called the cyclic polytope. And the important point is that for this set of polytopes, we know everything about the facets ahead of time. So for instance, when it's a polygon, you know that all the faces, all the edges are like 1, 2, 2, 3, 3, 4, 4, 5, and so on. And that generalizes, for example, in all the even dimensional cases, there are all these facets of the form II plus 1, JJ plus 1, KK plus 1, and so on. All right. So that's all you need to know about polytopes, and maybe I'll just have 5 minutes and I'll just flash through some of these 2 points. At least you understand what the conceptual points are. So now let's go back to the physics, and there's sort of 2 little surprises here. Is that there's some kind of hidden total positivity in just this, something as simple as this, the propagator with positive coefficients, 1 over Pn over m squared minus s, where the p's are positive and the m squareds are positive. And there's a hidden total positivity in the Legendre polynomials. And these things are going to be responsible for the infinitely many nonlinear equations that I told you about, and the fact that these higher dimension operators also have to lie inside specific polytopes. So let's talk about this hidden positivity associated with just the propagators here. So imagine I expand the amplitude, and just for simplicity, I've sent t to 0. So just imagine that I'm summing things that look like Pn over Mn squared minus s. And all I know is that Pn are positive and Mn squared is positive. The question is, what does that tell me about the coefficients in the expansion in powers of s? So let me just do it. Just trivially, I do it. I expand this out. And so all these coefficients, A0, A1, A2, blah, 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 are written as the sum of Pn over Mn squared, this is 1 over Mn squared, 1 over Mn squared squared, and so on. Okay? So, for instance, clearly they're all positive. All these A's are positive. And that was essentially the statement we made 14 years ago, which was also known to people in the 60s, right? In various guises. But much more is true. And it's because really what this is telling you is that these guys are in the convex hull of a particular curve, points on a particular curve. 1, x, x squared, x cubed, and so on. So I take a positive combination of points that look like this. If I knew the spectrum exactly ahead of time, then there would be a particular polytope. I don't even know the spectrum ahead of time, so I have to take the convex hull of this whole smooth curve. That's the one little extra novelty. Now, this is a famous curve, and it's also the most famous example of something that gives you positive minors, a cyclic polytope, and so on. Because if you just look at any determinants of d points on a curve like this, that determinant is trivial to calculate. It's a van der Waals determinant, and it's manifestly positive if the x's are ordered. So if you take any ordered points on the moment curve, then that gives you something whose convex hull is a cyclic polytope. It has this magical property that all the minors are positive. So that already tells you there has to be a big restriction on what these coefficients look like. And we worked out what the restriction is. Now, even in the continuum limit, it turns out it was also known to mathematicians in various guises in the past 10, 20 years. But here's the rule. So I'm now going to tell you the rule. What does it take, if and only if, property of these coefficients tell you that it can be expressed in this way? Okay? And here it is. This looks like a vector of numbers, but you actually make a matrix out of it. There's an associated matrix you make out of it, where you write down A0, A1, A2, blah, blah, A1, A2, A3, etc. This is called the Henkel matrix. The ij element of this matrix is the I plus jth vector element. Okay, so the claim is that in order for this to be in the convex hull of the moment curve, every minor of this matrix has to be positive. And it's if and only if. Okay? So the obvious statement that all these guys are positive is just about 1 by 1 minors. But everyone, that determinant is positive, that determinant is positive. You take any rows and columns of this matrix, ordered, they're all positive. So here's the first rather trivial example, but it's the first slightly non-trivial example. If I just take A0, A1, A2, the convex hull of 1x squared, then that's just the same as saying that these guys, and the x's are positive, importantly, that's the same as saying that we're somewhere inside the convex hull of this parabola up here. And so clearly, to be inside here, you have to have A1 is positive, but also A2 over A0 minus A1 over A0 squared is positive. That implies that. And that is indeed, that 1 by 1 minor and this big 2 by 2 minor of the Henkel matrix is a positive. All right. So that tells you an infinite number of nonlinear relations between higher dimension operators of different dimensionality. Okay? I could tell you more about when these bounds are saturated. They're saturated when what you're getting is tree-level exchange of a finite number of particles. And in fact, you measure how many particles there are by the size of the first matrix for which these determinants go to 0. They have to be positive if you're inside, so you can lie on the boundaries of some of these determinants are 0, and the size of the matrices where they hit 0 count the number of particles in the UV when it's exchanged at tree level. All right, now let me tell you a little bit about the hidden positivity of unitarity. So everybody knows that these Gegenbauer polynomials, these Lejeune polynomials, are just the square of 3-point amplitudes with the exchange of a spin s particle. And as such, in the forward limit, when cos theta goes to 1, these things are all positive. That's totally standard. And that's related to all the positivities we always talk about. But it's then natural to expand around the forward limit. So let me take these polynomials and expand around gs of 1 plus y. Let me collect all the Taylor coefficients together. So here's what it looks like. So here's the Taylor coefficient for spin 0, spin 1, spin 2. This is for Lejeune polynomials. It's something different in a different number of dimensions. All right. Now, there are some things that are obvious. For example, the top row is positive. That's just what we said. These things are positive in the forward limit. Something many people have observed is that not just the top row are positive, but all the numbers are positive. In other words, all the derivatives of those Lejeune or Gegenbauer polynomials in the forward limit are also positive. That was also observed by many people a long time ago. But the new observation is that this is a totally positive matrix. All the minors are positive. Okay? In the special cases where you just have cosines, so they're Chebyshev polynomials, this was known to Chebyshev in the 1850s. But the statement about general Lejeune polynomials and Gegenbauer polynomials is new and does not follow from that one. Okay, so that in particular means that if you take the top k rows of this matrix, then their convex hull is a cyclic polytope. And if we go back to this formula for the expansion of the amplitude, and I should have said that here, of course, there's also the U channel. So I'm doing a little toy example here with just the S channel just to illustrate the ideas. But in this formula, you see when I expand in T, I'm also picking out exactly the coefficients of the expansion of this Gegenbauer polynomial. And therefore, this positivity that we just discovered actually tells us that, and I'll skip this, this tells us that all of these higher dimension operators have to lie within a cyclic polytope. And when you include the U channel, that's if you only have the S channel. When you include the U channel, it turns out to be a half-dimensional projection of that underlying cyclic polytope to a new polytope, which is asymptotically looks cyclic, but some of the vertices at the bottom look a little bit different. But I'm just giving you the sort of basic ideas for where these things are coming from. So let me just finally show you some results, and then I'll stop. So these are now results where everything is done correctly. All the footnotes that I told you about are taken into account. And we're talking about, for example, pure photon scattering. So let's talk about photon scattering with these helicities. And I pull out the helicity pieces, and it's an expansion in powers of this variable z as s minus u and t. And so first, there's the nonlinear, those Henkel matrix consistency conditions. So I'm not talking about those. We talked about them already. But these are these polytope conditions. So for instance, for the coefficients of z squared and t squared, this is a one-dimensional space. And the bound tells us that the ratio of these couplings has got to be bigger than -7/20. Okay? That's a very specific number. And that 7/20 comes out of Lejeune polynomials. Okay? So had I not told you this, and I and I gave you something that violated that by a little bit. There's nothing obviously wrong with that, but no amount of tuning, nothing that you can do in the ultraviolet can violate that bound. Okay, so this is a sharp fact about higher dimension operators. And of course, you go on. In 2 dimensions, if I look at these coefficients, then the ratios of them live in a 2-dimensional space, and they have to lie inside this very, very specific polygon. And this is, and you'll notice that the vertices here are numbered, and these are actually what they're labeled by spin. So this is spin 4, spin 3, 5, 6, 7, 8. And so you see all the spins are vertices of this thing, but they accumulate as you go to infinity, and you have to lie inside this very specific polytope. You go to 3 dimensions, it lies inside a very specific 3-dimensional shape. And you might complain this shape looks, it looks kind of ugly and skinny, and it's very difficult for us to plot these things so they look big and fat, because the shapes are, the regions are actually surprisingly skinny. They're very narrow. So once you specify some of the couplings, the other ones tend to be incredibly tightly restricted. Okay? And I didn't show what it looks like here, but you can plot what you get from perturbative string theory at tree level, loop, some Euler-Heisenberg theory at loop level, many different examples, and they're all pretty close to each other and pretty close to the low spin boundaries here. Okay? So, all right. And this is what we get from pure graviton. Very similar story. There's a negative 1136 here instead. There's a very similar looking polygon in 2 dimensions and so on. So the moral is that the world is not a crappy metal. There's vastly greater UV constraints on IR physics than naively expected. And I remind you, this is all because of Lorentz invariance. Lorentz invariance and causality, together with unitarity. Unitarity is there for any theory, but it's Lorentz invariance and causality that give us all of this stuff. Okay? Now, just to end with 2 comments, can we include, this is not all the constraints that there are. And all we've done is just put in the most minimal thing of causality. For instance, there's all sorts of toy examples of amplitudes that I could write down of this form that would not have good behavior at high energy fixed angle. So I haven't really included the physics of UV completion in this analysis. Okay? So that's presumably going to put more constraints. It's surprising how constraining it is already, but that's presumably going to put even more constraints. And can we use these ideas to prove that, that higher dimension operators must always push the mass to charge ratio of extremal black holes negative? And for here, let me just make a comment in words at the end. If you talk about the higher dimension operators that contribute to the shift in the mass to charge ratio for black holes, there are operators that look like f to the 4th, operators that look like f squared r, and operators that look like r squared in the general number of dimensions, or maybe r squared phi if you have scalars lying around, even in 4 dimensions. And these things are, they're all of comparable size in an extremal black hole background, which is why they make a comparable shift, but they're very different from the status of what they do to scattering amplitudes. The f to the 4th is associated with the contact term of the 4-point amplitude, whereas, for example, f squared r is the wrong helicity 3-particle amplitude for 2 photons and a graviton. And the whole logic of all of this on-shell thinking is that the sort of 3-particle amplitudes are given, and then there are some constraints on 4-particle scattering from unitarity. However, there is one thing that you can do, and this is something that you know, we could have done 12 or whenever we wrote the weak gravity paper, which is just to check that the weak gravity conjecture is consistent under the renormalization group. Okay? And in other words, no matter what the higher dimension operators are, even if the theory is weakly coupled and the higher dimension operators are suppressed by m string, which is smaller than m Planck, if you wait long enough, the logarithmic corrections to the, for example, the f to the 4th term will dominate over whatever's sitting there at tree level already. Okay, so for big enough black holes, it doesn't matter. For big enough black holes, these higher dimension operators are dominated by the logs that are induced in the low energy theory. So you can ask whether the signs of the beta functions for those higher dimension operators are correct in order to push the mass charge ratio for extremal black holes down. And here's the cool thing. They are correct. And in fact, just for instance, the sign of the beta function for f to the fourth is always positive. Exactly what pushes the mass-to-charge ratio for extremal black holes down. But you might say, but what about supersymmetry? We know what, and this bugged me about the weak gravity conjecture from day one. Something that bugged me from day one is whatever the reason could be that would make the mass-to-charge ratio of extremal black holes go down, in supersymmetric theories they're BPS and they're protected. So how will this thing discover supersymmetry out of thin air? And here is the answer to the question. The gravitino is the unique particle that can make a wrong sign contribution to the beta function for this f to the fourth coupling. This is a counterpart to the statement that only non-abelian gauge fields can give you minus signs in the running of gauge couplings. So if you don't have gravitini around, the f to the fourth always goes in the right direction, and at one loop the f squared r doesn't run, so the f to the fourth dominates everything, and so weak gravity is asymptotically true. Okay? Only gravitini can give you a minus sign, and of course when you have gravitini, it's so incredibly constrained that, and in fact you only get 0 if you have enough supersymmetry. You only get 0 if you have n greater than or equal to 2 supersymmetry in 4 dimensions, when we can have BPS black holes. So there's a statement about the beta function for higher dimension operators that's saturated by supersymmetric theories. So that's the claim anyway. Asymptotically, the weak gravity conjecture is true. For large enough black holes, exponentially large black holes, just the running in the low energy theory forces the mass-to-charge ratio for extremal black holes down. So now, that doesn't say, so maybe it goes back up and down and does other complicated things in between. It would still be great to go back to weakly coupled theories, things where the higher dimension operators, the non-log pieces that really come from the UV are meaningful, and try to bound them as well. Okay? All right, that's it. Thank you.
Okay, we have a time for 1 or 2 short questions.
So you almost said that you could formalize naturalness at the beginning with these kind of ideas, but you didn't really say it.
Oh, I didn't say anything about naturalness.
You mentioned that you could constrain the typical sizes of the coefficients.
Oh, sorry. No, I just said, yeah. No, I just said that you might think it was only a matter of naturalness, and that you could violate it by making things by tuning. So I'm giving you examples of things which, like, take that, and it doesn't even seem that tuned. Like, take that negative 1136 or whatever the heck it was, right? And just say, I don't know, I wrote down my theory had it be, -3. Okay? So that doesn't even seem that bad, right? But I'm telling you, the -3, nothing you can ever do can get it to -3. You might think you tune this, you take that, add this spectrum, do this, do that, but there are just some things that are illegal. And so what I was trying to say is that, at least to my taste, if the science of distinguishing the swampland from the landscape is going to be interesting, it had better involve equal signs, okay? Because the squiggles are, the squiggles might be useful, to tell you what you're trying to prove with equal signs eventually. So I'm not saying you need equal signs to begin with, but it's not contentful if it permanently doesn't have equal signs, because that's the entire question, is whether things, are roughly, mostly true or impossible, right? Like take the practical question of whether you can find things that allow you to have Trans-Planckian traversal for inflation, right? That's a very, very practical question. And if there is something sharp there, it makes a big difference to say, well, it's very hard, very rare to get things that can traverse 10M Planck. But who gives a fuck? It's very hard, but then you can come up with a million anthropic reasons why it's very hard, but you need to do it. Otherwise, blah, 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 right? Big difference if it's hard or impossible, right? And so that's what I'm saying, that these things, now, I want to stress, nobody gives a rat's ass about these higher dimension operators, and I don't either, okay? We can't really measure them, well, maybe, anyway. I don't care about them, okay? I don't think anyone should really care about them that much. The only interest of and this is not yet interesting for any of the things that we care about phenomenologically. It's just an indication, though, that there are some tendrils coming down from the UV, that a lot more is going on in the IR following from consistency of the UV that you may have thought ahead of time. And that there are things lying around in familiar ancient objects, right? You know, there's something surprising in Legendre polynomials. There's something surprising in propagators, which is related to this. If with this casual inspection we can find things that have been, you know, unnoticed for 50 or 100 or 150 years, then I think we should look more carefully.
About your last comment about the gravitino,
yes.
Are you meaning that, for example, you can get the bounce on the mass of the gravitino because if
I'm
it's
just talking
too light?
about massless particles. You see, I'm just talking about massless particles here for my whole statement. If there's no weak coupling in the UV, then it happens right away. Okay? But if there's any weak coupling in the UV, so imagine the string scale is a little bit beneath the Planck scale, then there are really some higher dimension operators coming from integrand heavy string states suppressed by M string. Let's say F to the fourth operator suppressed by M string to the fourth. It was some power of G string on the front, but anyway, it's not M Planck to the fourth, right? It's alpha prime. So what I'm saying is that if you wait long enough, but F to the fourth is also induced by loops of photons and gravitons. That's induced at order 1 over M Planck to the fourth log, right? So there's a log running of F to the fourth coming from just gravity. And if you wait long enough, that log will eventually beat the tree level piece sitting there already, okay? So we have to go to exponentially large black holes. And so if anything is massless, if anything is massive, before you get that exponentially large, then it's not relevant, okay? So what I was trying to explain, though, is how it is that supersymmetric theories can appear in what I was saying is that if there's some kind of principle that tells you the mass to charge ratio for extreme black holes should go down, this principle is exactly violated for supersymmetric theories, where it's 0 exactly, right? And so somehow, whatever the statement had to be, it can't just be there's generically plus and minus signs, because it has to be such that it's always positive except when it's supersymmetric. So it had to discover supersymmetry somehow. And the answer to this question, at least for the log running part, is that the only things that can give you wrong signs for the beta function are gravitini.
Okay, let's thank Nima again. And remember, he'll be back for the colloquium.